Hello everyone, my name is Lena and I work with Dr. Christian Malaga and Dr. Mehdi Kashani at Imperial College London. Today I am presenting my paper on the application of buckling-enabled composite bracing to steel rocking frames. The way we currently design our buildings to withstand earthquakes is to allow some of the structural elements to dissipate seismic energy by sustaining damage at designated locations. This is done to avoid catastrophic structural failure, ensure a predictable failure mode, and minimize the casualties. However, these buildings undergo major damage during earthquakes and are often left unoperational and in need of significant repair or demolition. This leads to severe post-earthquake economic losses. My research looks at rocking frames, which are structures typically made of different elements tied together using unbonded post-tensioning. Since all the deformation is constricted between the connections, the damage to major structural members can be avoided. To improve the load resistance of these systems, elements that absorb modest amounts of seismic energy through damage are still included. Some common examples include yielding seat angles, yielding web hourglass pins, beam, web, or flange friction devices, and yielding thin steel plate infill walls. As the name suggests, these elements sustain damage and require replacement after seismic events. Some of these elements are embedded within the structural members and can be very difficult to access. We again get a system with limited durability that requires frequent inspections. And even with these technologies, many structures still experience permanent damage. Following this, the objective of this paper was to explore a passive damage avoidance solution that enhances the seismic performance of steel rocking frames. Our approach to this damage avoidance solution was to use an element that can absorb some seismic energy and after a critical load provide significant global buckling without experiencing any permanent deformation. This is more commonly known as elastic buckling. The behavior of these elements is comparable to the elastic buckling exhibited by a typical steel tape measure. The response of these buckling-enabled braces would depend strongly on the material selection. We selected GFRP due to its low strength-to-weight ratio and its ability to undergo significant elastic buckling. The benchmark building selected was the three-story steel moment-resisting frame proposed by the Structural Control Committee of the American Society of Civil Engineers for the SAC Steel project. The structure's geometric and member details are presented here. The building represents a typical low-rise structure with an aspect ratio of 0.3. The rocking frame counterparts employed identical sections as the moment frame with rocking connections at both the beam column and column foundation interfaces. To provide support for the buckling-enabled bracing at ground level, a floor beam was provided. A tendon cross-section of 500 square millimeters was incorporated for the beams and columns. For configuration 2, buckling-enabled bracing elements were incorporated in two bays of the building. The Finite Element program OpenSeas was utilized for all numerical analysis. Force-based nonlinear beam column elements were used for the beams and the columns. A steel O1 material model was employed for the fiber sections with their respective yield strengths. Geometric nonlinearities were accounted for by means of a co-rotational transformation. A constant stiffness proportional damping of 5% was specified for all models. The post-tensioning tendons were modeled using co-rotational truss elements with an initial stress uniaxial material. Zero-length gap elements, or springs, were used to simulate the rocking interactions. Lobato integration scheme was used to determine the distribution of the gap elements along the member edges. Elastic perfectly plastic material with no tension stiffness was defined for the gap element. And finally, the columns and tendons were modeled as continuous elements along the frame heights. The bracing elements were first simulated in Abacus before being implemented into the OpenSeas models. We can see the geometric parameters of the bracing elements here. A circular arc shape was selected for the elements to increase the buckling strength. An imperfection amplitude equal to the element thickness was specified for each brace to induce buckling along the negative y-axis. An isotropic elastic material with modulus of 18 GPa and Poisson's ratio of 0.3 for GFRP was used to simulate each BECB element in Abacus in order to obtain the respective buckling response. Elastic bilinear uniaxial material was used to represent the pre to post buckling behavior of BECB in OpenSeas. Finally, the bracing elements were represented as truss compression-only elements in the numerical models. First, a static pushover analysis was performed. A displacement control strategy was used to perform the nonlinear static analysis. The lateral resistance of the rocking frame without the buckling-enabled bracing elements was 55% lower than the moment-resisting frame. Rocking frames with buckling-enabled bracing elements exhibited a 30% increase in the lateral load resistance, whereas configuration 2 showed a 63% increase compared to the rocking frames. In comparison with the moment-resisting frames, the lateral capacity of the rocking frames with these buckling-enabled bracing elements was 20% lower, whereas for the second configuration, it was 15% higher. Additionally, all the rocking frames exhibited zero residual drifts and damage accumulation for higher drift limits compared to the moment-resisting frame. The out-of-plane displacements of the bracings were then plotted with respect to the frame drifts. It can be observed that for both configurations, there is a change in slope at approximately 2.5% drift where the member deflections increase at a greater rate. A maximum deflection of 45 millimeters in configuration 1 and 30 millimeters in configuration 2 is experienced by the longer buckling-enabled bracing elements on the first floor prior to reaching the 2.5% drift. It is important to mention that the buckling-enabled bracing system allows for the tuning of this limit. Furthermore, a maximum deflection of 330 millimeter at 10% drift was observed on the first floor in the longer buckling-enabled bracing element associated with configuration 1. In configuration 2, the maximum deflections for both the longer and shorter members were noted on the first floor, with longer members reaching 200 millimeters and shorter members reaching 100 millimeters. Frequency response functions were then generated using discrete sine sweep input ground motions to provide insight into the complex dynamic behavior of these nonlinear structural systems. These FRFs were also utilized to identify the fundamental frequencies of the building models using the maximum inflection points of the low amplitude curves. The FRFs presented here are plotted in terms of roof accelerations. It can be observed that the natural frequency of the MRF is 1 Hz, whereas the rocking frame is 0.7 Hz. In comparison, the fundamental frequencies of the rocking frame with buckling-enabled bracing in configuration 1 was 1.5 Hz and in configuration 2 was 2 Hz, respectively. Therefore, it is apparent that both configurations of the buckling-enabled braced frames are stiffer than their pure rocking frame counterpart. Contrary to the rocking structures, the fundamental frequency of the moment-resisting frame is constant along all forcing amplitudes until yielding. This is due to the nonlinearity of the rocking system. It is also apparent that the rocking frame has greater flexibility than its moment-resisting frame counterpart, which is expected. Moreover, it can be observed that the maximum story acceleration for the rocking frame for high amplitude excitations are 55% greater than the moment-resisting frame. The rocking frame with buckling-enabled bracing elements exhibited accelerations that were 25% higher than the moment-resisting frame, whereas the accelerations for configuration 2 were very close, about 2% higher to the moment-resisting frame. Finally, it is clear that steel rocking frames equipped with buckling-enabled bracing result in significantly lower peak response quantities compared with systems without the buckling-enabled elements, and close to those exhibited by a conventional steel moment-resisting frame. Besides, buckling-enabled bracing was also observed to enhance the overall stability of the rocking structure, and numerical convergence during the analysis was achieved significantly quicker. The effectiveness of the buckling-enabled bracing was finally evaluated by subjecting the buildings to a set of real earthquake records and developing the IDA curves. The peak interstory drift ratio was adopted as the damage measure, while the spectral acceleration at the fundamental period of each respective building was selected as the intensity measure. The 22 far-field earthquake records detailed in the FEMA P695 report and obtained from the peer database were employed. A conventional steel moment-resisting frame has an IDA curve that softens after yielding and accelerates towards larger drifts. The curve then flattens out in a plateau of the IM with the DM moving forward towards infinity, indicating dynamic instability. In contrast, the IDA curves for rocking frames can be characterized by a weaving behavior, where the buildings exhibit successive softening and hardening segments. This is expected due to the inherent nonlinear relationship between the applied forces and response of the rocking structural system. Moreover, nonlinear structures typically exhibit coexisting amplitude responses at and around the system's nonlinear resonances. Likewise, the influence of subharmonic resonances and higher mode effects on the structural response also increases with higher amplitude IMs. Overall, both configurations with the buckling-enabled bracing elements consistently exhibited lower relative DM at the same IM in comparison to the rocking frame and the moment frame buildings. The rocking frame structures also experienced minor hardening following the engagement of the buckling-enabled bracing system for the majority of the records. Among the initial rocking frame with buckling-enabled bracing models, the third-story beams in the second and third bays experienced yielding. This was due to the additional forces induced on the beam by the buckling-enabled bracing members during their compressive cycles. Additionally, yielding due to the high compressive forces in the buckling-enabled bracing members was also initially identified in the mid-bay column on the first story for configuration 2. In addition, member yielding led to higher deflections in the connected BECB members, resulting in the fracture of the longer braces on the first story. Following these observations, the yielded elements for the rocking frames with BECB were strengthened by increasing section sizes to accommodate the additional forces. The results presented herein reflect the response of the modified models. In the revised models, the strains in the BCB elements remained below their fracture limits, and the collapse was primarily governed by the performance of the post-tensioning strands. A deflection of 360 millimeters at collapse was experienced by the longer BCB elements in configuration 1, which is slightly higher than that observed during the static analysis. A deflection of 300 millimeters at collapse was experienced by the longer BCB elements in configuration 2, which is also higher than that observed at 8% drift during the static analysis. The median IDA curves comparing the four buildings are presented here. It can be observed that the IDA curves of the frames with the buckling-enabled bracing exhibited higher elastic slopes, indicating a stiffer structure than the moment frame and the rocking frame. Moreover, both configurations with the buckling-enabled bracing remained elastic for greater drifts than the other structures. The global collapse for configuration 2 occurred at 9% drift, whereas for configuration 1 it was at 7% drift. The elastic plastic transition for the rocking frames was primarily characterized by the yielding of the post-tensioning. The first post-tensioning strands to experience damage was the beam post-tensioning on the first floor for all rocking frames. This can be attributed to the greater beam rotations at the first level, which imposes an additional bending moment on the column, thereby leading to higher demands. These greater rotations are the results of connection asymmetry at the first level of the building, with base rocking at the ground level and a continuous connection at the first story. This characteristic is unique to rocking frames and has been discussed in our previous papers. For this reason, special design requirements are needed for the post-tensioning strands on the first and second stories. Fragility curves were then derived from the IDEA results using maximum interstory drifts and story accelerations to assess the structural performance of rocking frame structures for different objectives. The structural performance levels were selected based on recommendations from FEMA 273 for steel moment frames, which included collapse prevention, life safety, and immediate occupancy at 0.7% drift, which is presented here. Moreover, a peak floor acceleration limit of 0.5 g was used as an additional limit state. It is important to note that these damage limit states do not directly apply to the rocking frame with buckling-enabled bracing because the proposed structural configuration did not experience any damage until the 4 to 4.5% drift limit. However, these performance objectives can provide context for the expected damage levels in a conventional moment-resisting frame building. It can be noted from these figures that buildings with buckling-enabled bracing demonstrated lower probabilities of exceedance than the moment-resisting frame for both damage limit states, particularly at high seismic intensities. The configuration 1 of the rocking frame evidenced the best overall combination of demand reduction and performance probabilities among all cases. The self-centering performance of this frame can be further improved by increasing the post-tensioning on the first and second stories. In summary, this study has assessed the feasibility of incorporating buckling-enabled composite bracing elements into steel rocking frames to enhance their lateral load-carrying capacity and stability. The knowledge gained through these investigations will lead towards the provision of practical design guidelines for post-tension steel rocking frames with buckling-enabled composite bracing. In the study, we learned that first, both configurations of the buckling-enabled brace frames were 1.5 to 2 times stiffer than their pure rocking frame and moment-resisting frame counterparts. Second, the rocking frame with buckling-enabled bracing exhibited maximum story accelerations and drifts that were very close to those experienced by the moment-resisting frame. Both buildings with the buckling-enabled bracing remained elastic for drifts higher than those for the moment-resisting frame. Finally, the results demonstrated that the buckling-enabled systems have enhanced performance due to lower probabilities of exceedance for all damage limit states considered, specifically at higher ground motion intensities. It is important to note that the proposed buckling-enabled brace system relies on the controlled elastic buckling of GFRP members that do not accumulate any plastic strains. Therefore, it is crucial that a compression-only response is ensured. This brings us to the end of this presentation. Thank you very much for listening.